A z-score is a measure of relative standing. We can use z-scores to compare data values from two different distributions. So the z-score of a data value is the number of standard deviations that the data value is above or below the mean. So our formula for the z-score is that z is equal to the data value minus the mean divided by the standard deviation. That's if we were talking about a data value and we had the population mean and the population standard deviation, or we could just use slightly different notation. The z-score could be the data value minus the mean divided by the standard deviation s, and that's just if we're using from a set of data that was a sample. So remember that the mean can be given by mu or x bar. That's the mean, depending on whether we're talking about a population or a sample. And the standard deviation can be given by sigma or by s. That's the standard deviation. And little x is always our data value. So the number of standard deviations above or below the mean. So for example, in 2015, SAT scores had a mean of 1,006 and a standard deviation of 236. So if Ty took that SAT and got a 1430, what is the z-score for his exam? And was his z-score or was his exam score unusual? Was it unusually high or unusually low? So let's first just find the z-score. So the z-score is the data value minus the mean divided by the standard deviation. We use mu and sigma this time because this was the mean and standard deviation of all of the SATs given in 2015. So that's a population. And in our case, the data value is the actual data value we're interested in, Ty's score. That's 1430 minus the mean for the distribution. That's 1,006 divided by the standard deviation for the distribution, 236. And so we can just calculate those values. And if we throw that into a calculator, we've got, or just subtract ourselves, we've got 424 divided by 236, and now probably using a calculator to divide that, we've got 1.797. So that is our z-score, 1.797, and that's telling us that Ty's SAT score was almost 2 standard deviations above the mean, but not quite. So was his score unusual? No. Remember that our definition of unusual is more than 2 standard deviations outside of the mean. So more than 2 standard deviations away from the mean. And so this is saying that Ty's score was 1.797 standard deviations above the mean. So not quite 2 standard deviations above the mean. If it was, say, a z-score of 2.3 or something like that, that would be more than 2 standard deviations above the mean. So we would say no, his score wasn't unusual. It was less than 2 standard deviations above the mean. Okay. So why don't you try a similar example? Here, though, we're also going to compare data values from 2 different distributions, which z-scores are especially good for. So in 2015, as we have above, SAT scores had a mean of 1,006 and a standard deviation of 236, whereas ACTs, that's another college entrance exam that's more common in the Midwest, ACTs had a mean of 21.1 and a standard deviation of 4.8. So if Alfie took the SAT and got an 890, and Ben took the ACT and got a 19, then I'd like you to find the z-score for each exam, try to figure out who had a better score based on that, and then answer, were either of those scores unusual? So pause and try that out, and we'll talk about it in just a moment. Okay, so taking a look at this example, we first want to find the z-score for each exam. So we can find Alfie's z-score, and the z-score is, again, the data value minus the mean divided by the standard deviation. So in this case, that's Alfie's exam, an 890, minus the mean for the distribution, 1006, divided by the standard deviation of 236. And so that will give us a negative 116 divided by 236. And so we'll have a negative z-score in this case, a negative 0.49. So that is telling us that Alfie's z-score is about half of a standard deviation below the mean, whereas Ben's z-score is still the data value minus the mean divided by the standard deviation, but now we've got a new mean and a new standard deviation because Ben was taking the ACT instead. So Ben had a 19 minus the mean is a 21.1 divided by a standard deviation of 4.8. And so that's a negative 2.1 divided by 4.8. And when we divide, we get negative 0.437. So those are the z-scores for each of the exams. So both of these were about half a standard deviation below the mean. This was a little bit farther below the mean, and this was not quite as far below the mean. Okay, so who had a better score? So thinking about these exams, we've got the mean for the SAT, and the mean there was 1006. We've got the mean for the ACT, and the mean there is 21.1. And then we have our scores for Alfie and Ben. We see that Alfie had a 890, and Ben had a 19. And what we've done when we take these z-scores is translate both of these down to one single distribution. We translate these both down to a z-score. And again, the z-score, it's the number of standard deviations above or below the mean. So both of these values, both the 21.1 and the 1006, would translate to a z-score of 0, right? Because they are exactly at the mean. They are 0 standard deviations above or below the mean because they are equal to the mean. So that's a 0. And what we found out by taking these z-scores is that Ben's score translates to a negative 0.437, and Alfie's z-score translates to a negative 0.49. So these are really close to each other. They're not super different, negative 0.49. But Alfie's score is a little lower on the scale. So Alfie's score is lower. It is more standard deviations below the mean. And so Alfie did not have as good of a score, and we would say that that Ben had a better score. So Ben had a better score. It was higher on the z-scale. It was not as many standard deviations below the mean. Also notice anytime we're taking a z-score of a value that's below the mean, we're going to have a negative value, as we did in both cases here. Anytime we took a z-score of a value that was above the mean, we would have a positive z-score. And finally, were either of these scores unusual? No. Both were less than one standard deviation of the mean, less than one standard deviation away from the mean. So both less than 2 standard deviations from the mean. So basically, a z-score of 2 or larger will be unusual, and a z-score of negative 2 or smaller will be unusual. So z-score of less than or equal to negative 2 is unusual, and greater than positive 2 is unusual. And I want to reinforce an idea that we saw above when we took one distribution and mapped it onto another. So when we thought about, say the SAT scores, and said, okay, 1006 was the average, and we know what the standard deviation is, and we mapped it down using a z-score, down to 1006 would map to 0, and because the SAT has a standard deviation of, I think it was 236, subtracting 236 from 1006 would give us 770, and subtracting another 236 off would give us 534. So this 770 is one standard deviation below the mean, and because it's below the mean, that would be a z-score of -1. 534 is 2 standard deviations below the mean, so that would be a z-score of -2. If we went in the other direction, if we added the z-score of 236 to 1006, we would have 1242, and that would map down to a z-score of +1 because it's 1 standard deviation above the mean. And if we added another standard deviation, if we added 236 again to that value, we'd have 1478, and that would map down to a z-score of +2 because it's 2 standard deviations above the mean. And similarly, if we're looking at some different distribution, like the ACTs from that year, again, the mean was 21.1, so that would map to 0 standard deviations above or below the mean. That would map to a z-score of 0. If we added 1 standard deviation, the standard deviation for the ACTs, at least according to the above problem, was 4.8. So if we add 4.8 to that, we'll have 25.9, and that corresponds to a z-score of 1. If we add another 4.8 to that, we'll have 30.7, and now we're 2 standard deviations above the mean. If we go the other direction, if we subtract 4.8 from 21.1, we'll have 16.3, and that's 1 standard deviation below the mean, so a z-score of -1. And subtract another 4.8, another standard deviation from that, we'll get 11.5, and that's 2 standard deviations below the mean, so that would give us a z-score of -2. So a z-score takes any distribution and maps it onto the same distribution with a mean of 0 and a standard deviation of 1. Here with the cats, we just see that again. Here in this column, those are the z-scores that we see there. So this is the mean, a z-score of 0. This is 12.4. It's 1 z-score above the mean. So it's a z-score of 1, or 1 standard deviation above the mean, 2 standard deviations above the mean, and so on. 1 standard deviation below the mean, and so on. So one thing that's really great about a z-score is that it can be used to get an idea of relative standing without knowing that much about the details of the measurement. So especially in health sciences, this can be really useful. If you get some kind of information like, the red blood cell count in my body is 48 micrograms per microliter, blah, blah, blah. You could get that information and say, well, that doesn't mean anything to me. Is that good? Is that bad? Is that normal? But a lot of health parameters are actually given either as z-scores or as t-scores, which is a very similar thing, a t-distribution, which we'll talk about later in the course. But both are essentially the number of standard deviations that the data value is above or below the mean. So say, for example, you got a z-score of -2.5 for your bone density. Well, without knowing anything about, what the details of that measurement are, knowing that the z-score was -2.5 tells you right away that where the relative standing of your bone density is, that you were 2.5 standard deviations below the mean, and anything more than 2 standard deviations below the mean is unusually low. So you could infer from that you had low bone density for your age, which might mean, oh, I should start really worrying about calcium or whatever else I might need to do to think about bone density. So instead of thinking about the really specifics of the measurement, which might not mean anything to you if you're in that field, having a z-score tells you, am I above the mean? Am I below the mean? How far above or below the mean am I? 68% of the data falls within one standard deviation of the mean, so anything between -1 and 1 is essentially normal, and anything outside of -2 and +2 is unusual. Okay, let's do one more example together. So suppose that the lifespans of hamsters are normally distributed with a mean of 3.4 years and a standard deviation of 0.9 years, and the lifespans of cats are normally distributed with a mean of 13.2 years and a standard deviation of 1.8 years. If Haley's cat lived to be 17 and her hamster lived to be 5, who lived a relatively longer life compared with others of their species, and are either of their lifespans unusually long? So take a moment to think about that. We'll talk about it together. Okay, so let's first find the z-scores for each value. So for the hamster, our z-score would be the data value minus the mean divided by the standard deviation. In that case, that's 5 minus 3.4 divided by 0.9. And so if we divided that out, we would get 1.78 for the z-score for the hamster. And for the cat, we would have a z-score. Z is equal to the data value minus the mean divided by the standard deviation. And that's equal to 17 was the data value, the cat we're interested in, minus the mean for the distribution, 13.2, divided by the standard deviation, 1.8. And we could calculate that out to be 2.1. So we got a z-score of 1.78, a z-score of 2.1. And so we figured out that in terms of z-scores and ages, both of these animals live to be relatively old, as we could tell from the numbers to begin with. But z-score 0, 1, 2. One of them was a little bit above 2. So the cat had a z-score of 2.1, and that was the cat. And our hamster had a z-score of 1.78. So we would say that relatively, the cat lived a longer life compared with others of its species. Its lifespan was more than 2 standard deviations above the mean. So cat lived relatively longer. And were either of their lifespans unusually long? Yes, the cat's lifespan had a z-score of 2.1. So its z-score of 2.1 was greater than 2. And so this was unusually long. Whereas the hamster's lifespan was between -2 and +2. It was not unusually long or short. It was within the 95% of the rest of the data.